In section 7.3, we're going to learn about a new distribution. It's called the chi-square distribution. And the symbol, so for the normal curve we use z, for the t-distribution we use t, for the chi-square we use the Greek letter chi. It looks like an x with a tail on the top, and then a square, so x to the second. That's called the chi-square distribution. And it's going to be good for things like calculating confidence intervals for standard deviations and variances. So we're going to use this for confidence intervals for sigmas and sigma squareds. Okay, used for. And the reason we use it for standard deviations and variances is because unlike the mean, mu, sigmas and sigma squares, when you plot them, tend to be skewed. So the data, if you take a bunch of standard deviations or variances of a bunch of samples and you were to plot them, their histograms would look skewed. So the normality requirement for a confidence interval estimate of sigma is stricter than the normality requirement for a confidence interval estimate of mu. Departures from normality have a greater effect on confidence interval estimates of sigma than on confidence interval estimates of mu. That is, a confidence interval estimate of sigma is less robust against a departure from normality than a confidence. So back in 7.2, I believe, we said, maybe even 7.1, we said, oh, if you plot your histogram of your mu's and it's skewed, you can still proceed. Well, in this one, we're going to make it that we want these variances and standard deviations when you plot them in histogram to be as close to normal as you can get. Okay, so let's look at 22. So in this one, we'll actually do some computations using this new system, this new curve. So it says, use the given information to find the number of degrees of freedom, the critical values chi-squared left and chi-squared right. So I'll explain what these symbols mean in a minute. And the confidence interval estimate of the standard deviation. It is reasonable to assume that a simple random sample has been selected from a population with a normal distribution. So we have a normal distribution. So that means we can proceed with this test. We don't have to look and see if the data is normally distributed or not. So it says nicotine in menthol cigarettes, 80% confidence, N is 22, and the standard deviation is 0.22 milligrams. So they're looking at kind of the variation of milligrams of nicotine in 22 different cigarettes. Okay, so first question says, what's the degrees of freedom? Well, the degrees of freedom, df, is the same as in the last section. It's just n minus 1. So in this problem, n is 22, so df is 21. Okay, now to understand the next part, it's probably best to use a picture. In fact, let me use some white space up here to describe, generally speaking, what a chi-square distribution looks like. So this distribution is skewed right. So it looks something like that. But just like the t-distribution, this distribution also changes shape as your sample size gets bigger. So it becomes less skewed as your n increases. So this would be like a n of, let's say this is an n of 5 right here. And this one's an n of, we'll say 20. And then this one's an n of 50. So like the t-distribution, we can have small n's. And like the t-distribution, as n increases, it becomes more and more like the normal curve. But this one has two measures. So just like in the normal curve, when we tried to find areas in the curve, if we had to look at areas between two flags, we would have two z-scores. Same thing here. So if I want to look at, let me draw this, not on this curve, let me draw it over here. Let's say we want to be, let's use this problem as an example. So let's say we want to be 80% confident. That means there is a chi-squared right value. So this R stands for right. And there's a chi-squared left value, where L is left, that separates, in this problem, your confidence level. And then the area in this tail would be half of your alpha value, and the area in this tail would be half of the alpha value. So we've seen this before. It's the exact same concept as for the t distribution or the z distribution. I have a confidence level. These two critical values will demarcate the lower and the upper values. And then the alpha is how much I'm not confident. So I put half of that area in the left tail, half of that area in the right tail. So for our problem here, we want to be 80% confident right here. So let's write 80% confident would mean alpha, the amount we're not confident, is 20%. And alpha over 2 is 10%. And so let's draw the specific picture for this problem. I've got the chi-squared generally, and then I'm going to have a chi-squared left here and a chi-squared right here. This area between these two flags is 0.80, which means there's 0.10 here and 0.10 here. So 10% in my area, my number might be, the true number might be smaller than what I would guess. 80% chance that the true number is in between what we had guessed, and 10% chance that the actual number is bigger than what we had guessed. And these three numbers should always add to 1.0 or 100%. So now, just like before, this becomes a table lookup problem. So we're going to go, and you'll have a table like this in the back of your notes. So it's called the chi-squared table. And just like, actually not quite just like, in this table, your first 5 columns are for chi-squared left values. And the way this works is, for the chi-squared left value, you look at how much area is to the right. So unfortunately, in almost all the tables we've used, they're using areas to the left. This is one where you use area to the right. So if I'm at chi-squared left, let me see if I can show this at this, yeah. If I'm at chi-squared left, there's 10% of the area to the left, but this table wants the area to the right. So the area to the right of this value here is 90. The 0.8 plus the 0.10. So there's 0.90 to the right. So we're going to be in this column. Okay, now for chi-squared right, it's the area to the right of it, and that's clearly just this 10%. So we're going to be in this column. Okay, so we know which columns we're in. Now we just have to look at the degrees of freedom. So we said the degrees of freedom in this problem was 21. So we're going to go down df of 21. Can I show it on screen? Barely. So here's degrees of freedom 21. And we're just going to go over to those 2 columns that we circled. So chi-squared left, 90% of the area to the right, 21 degrees of freedom. The value is 13.240. So chi-squared left right here, 13.240, and I'll write it here too so we can see it, 13.240. Okay, now chi-squared right at 21 degrees of freedom would be right, so this column from before, 10% of the area is to the right of it, and then I go down to 21 degrees of freedom, and where those two things intersect, 29.615. 29.615. So this axis starts over here at 0, and then chi-squareds just increase as you go to the right. So chi-squared right, if we've done this correctly, should be bigger than chi-squared left. Okay, so that first part's hopefully easy. It's just a table lookup. The next part is trickier because we have to now do the confidence interval. So the confidence interval for the standard deviation looks like this. We have the square root of n minus 1, which is just your degrees of freedom, times the sample standard deviation squared, all divided by the chi-squared right value. And keep in mind, this 2 here does not mean I square the number. So when I see chi r2, it's just this number we just looked up. Okay, so that is the lower limit. That's going to sandwich our sigma, the population standard deviation, which is sandwiched on the upper bound by n minus 1 times s squared, same numerator. The only thing that changes is the denominator becomes chi squared left. And that's the main equation we need today. So let's see how that will work for our problem. So plugging in our numbers, we would have 22 minus 1 times s, which is 0.22, squared, all divided by chi-squared right, which was 29.615, and then take a square root, which will sandwich sigma, which is sandwiched by the same numbers on top, 22 minus 1 times 0.22 squared, all divided by chi-squared left, which is 13.240. And if you are very careful in how you punch this in your calculator, you should get, for this problem, 0.1853 sandwiches the population standard deviation is sandwiched by 0.2771. And then they want us to round to 2 decimal places, so we'll call it 0.19 and 0.28. And right out the gate, we've just done the hardest math we will do for this section. So that's what you have to do. And we'll just see a couple more examples where we repeat this process. And then finally, what can we say? Well, we could say we are 80% confident that the variation, let me say this carefully, we are 80% confident that the standard deviation of all cigarettes, not just the 22 we use in the sample, is between 0.19 milligrams of nicotine and 0.28 milligrams of nicotine. And even that, saying all cigarettes, you have to be a little careful. It'd probably be just the cigarettes manufactured by whatever company's making these. Okay, let's try 23 and see this again. So we would have a simple random sample from a population with a normal distribution. So because it says that, we can proceed, of 98 body temperatures. So N is 98, which means degrees of freedom is 97. Subtract 1 from that. Has a mean of 98.7 and a standard deviation of 0.68. So notice in no place in here did we write x bar, the mean, so we don't need that number. S is 0.68. Construct 95% confidence interval. So our confidence level is 0.95, which means alpha is 0.05, which means alpha over 2 is 0.025. And that's everything we need. So why don't I'll still draw the picture just so we can see it though, so we can get used to this. So we're going to have our right skewed chi-squared. If our confidence level is 0.95, that means between this flag and this flag is 0.95. This upper area would be 0.025, the alpha over 2. And this area down here is 0.025. This is chi-squared left. This is chi-squared right. And now we can look those up. So I wonder if I have a clean one here. Yeah, let me use this clean one. Okay, so again, the first I'll try to show just the picture in the table. So the first 5 columns are specifically for chi-squared left, and the second 5 columns are specifically for chi-squared right. Now, chi-squared left, you have to do a little math here. The area to the right of it is 0.95 plus 0.025, so it's actually 0.975. So it's actually this column right here, 0.975, right in the middle. Chi-squared right would be equal to this alpha over 2, so it would be 0.025 right in the middle. Now you'll notice, if you do this correctly, the columns that you circle will be exactly in the same spot. This one's in the middle, this one's in the middle. Now we go down these middle columns until we hit a degree of freedom of 97, because our degrees of freedom was 97 here. And so we would get, right in the middle columns here, and you notice it goes from 90 to 100. So for us, you're just going to pick the one closest to your number. So we wanted 97. The table stops at 100. So let's just take the 100 values right in the middle. So chi-squared left is 74.222, and chi-squared right is 129.561. Those two values right there. Okay, so let me write those. Chi-squared left was 74.222, and chi-squared right was 129.561. Okay, now we will use that same equation we used before right here. So we know the chi-squared right and left values. We just wrote them down. We know n in this problem is 98. We know s in this problem is 0.68. So we would plug those in. It would look like this. Square root 98 minus 1 times s squared, so times 0.68 squared, all divided by chi-squared right, which is 129.561. That's going to sandwich standard deviation, which is sandwiched by almost the same thing. 98 minus 1 times 0.68 squared, same top, divided by chi-squared left now, 74.222. And again, if you're careful when you do this in your calculator, you should get that this becomes 0.5883, and the right side is 0.7774. rounded to 2 decimal places, we would say 0.59 and 0.78. So they looked at 98 body temperatures, and they found the mean to be 98.7 and the standard deviation to be 0.68. And with that information, we can say we are 95% confident that of all people, their body temperature's standard deviation is between 0.59 degrees Fahrenheit and 0.78 degrees Fahrenheit. Okay, let's look at 24. Goes. Okay, 24. This one's going to include actual data, so we can't solve it with just the table lookup and everything. And you could, but you'd have to calculate the sample standard deviation yourself. It'd be more work. So like I've done in the past, I'm going to give you the steps to just let the computer do the work for you. So we have 12 different video games showing substance use were observed and the duration of times of gameplay in seconds are listed below. The design of the study justifies the assumption that the sample can be treated as a simple random sample. Use the sample data to construct 80% confidence interval. Let's circle that. 80% confidence interval estimate of the standard deviation of the duration times of gameplay. Assume that this sample is obtained from a population with a normal distribution. Okay, I need to see those words, otherwise you really shouldn't be doing this test. But we saw them, so we're good. So next to these numbers, there'll be a little window in a window button. We've seen it many times. So you're going to click that. You're going to say open in StatCrunch. You're going to go to Stat button. Then you'll click on Variance Stats from the drop-down. You'll select one sample. Then you'll click With Data, because this one has the data already there. Then you'll click Variable 1, the words Variable 1, to load these numbers into this computer. Then there will be a confidence interval for sigma squared. So the words similar to this will appear on the computer. Say confidence interval for sigma squared. And you have to change it to the number that we had. So I think it defaults to 0.95. You'll want to change that number to 0.80, the confidence level for our problem. And then you'll hit compute. And then you'll get a table, and the table will have lots of information in it, but it will give you the confidence interval. So it will say the words L period limit for the lower limit of your confidence interval, and it will give you the words U period limit for the upper limit box. So you're going to look in those two boxes. The lower limit box for my problem with these numbers will say something like this: 71694.37. And the upper limit will say 222.045.3. Now here's the gotcha, is that we want the interval for the standard deviation, sigma. But what the computer is going to calculate is variance, sigma squared. So this is the limit on sigma squared. But we want the limit of sigma. So to do this, you just have to take the square root of these numbers that they give you. So you have to take a square root of those two numbers. And if you do that, you should get the answer 267.76 sandwiches, standard deviation, sandwiched by 471.22. And then for the final answer, it says round to 1 decimal. So we'll say 267.8 and 471.2. And so again, let's try to interpret this. So this means the standard deviation of playtime of all video games where the playtime shows violence is between 267.8 seconds and 471.2 seconds. Okay, so if you have the computer steps for this one, it's really not bad, but the gotcha there is just don't forget to square root your answers, otherwise you'll get them wrong. So take a square root, then round, and you should get them. Okay, 25. This is a problem we've seen several times in this course. We've studied it in different ways. This is the bank teller problem. So I go to the bank and I can either stay in a single line or I can go into multiple lines, and we want to see which one has more variation. In fact, this one has, in Bank A, customers enter a single waiting line that feeds 3 tellers. At Bank B, customers may enter any of 3 different lines that have formed at 3 teller windows. So Bank B is more like a grocery store. You can pick the checkout. Okay, so in this problem, it's the exact same steps as 24. So you have to do this with a computer. I'm just going to write same steps as 24. But you have to do it twice. So you do it once for Bank A numbers, and then you do the same steps for Bank B numbers. Once for A, once for B. And again, you're going to get numbers that you have to take square roots of. So for Bank A, for these numbers up here, you're going to get something like 0.11 sandwiches sigma squared sandwiches 1.496. And then you're going to square root those numbers. So you're going to take the square root of 0.11 and the square root of 1.496. And then that should sandwich standard deviation, not variance. So if you square root these numbers, you should get 0.33 and 1.22. Oh, and notice that they want a 99% confidence level. So that step where you have to change the confidence level here, in this problem it's going to be 0.99. So we have 0.33 here and 1.22 here. Okay, then for B, well, for B it's going to be the same steps. So you're going to get 2 numbers, then you take a square root of them, and then you round, and what you should get if you've done it correctly is, for this problem, 1.12 and 4.12. Because for B, I'll just give you one step of it. You would have gotten from the printout 1.248 and 16.974. So square root of these 2 numbers gives you these 2 numbers. And now we can reprove what we proved earlier. We saw this with when we looked at it a different way, is that the variation at Bank B is much larger. So the standard deviation and waiting times at Bank B, you might wait an extra minute or you might wait an extra 4 minutes. At Bank A, you might only have to wait an extra 0.3 minutes or 1.22 minutes. So Bank B has more variation in it. And the way we would say it is, the variation appears to be significantly lower with a single line system. Okay, that's the end of the kind of challenging problems. The next two are kind of very simple. And then the rest are vocab word checks. Okay, so 26, assume that the sample is a simple random sample obtained from a normally distributed population of IQ scores of statistics professors. Use the table below to find the minimum sample size needed to be 99% confident that the sample standard deviation S is within 50% of sigma. So we've seen calculating sample size in the past two sections, and we had a different equation for both of those. And the equations weren't very simple. Because the chi-square distribution is so complicated, we're not going to use an equation to calculate sample size. We're going to use a table lookup. So this is very simple. You go to the 99% confident row. So there's only two rows, 95 or 99. So we're in this row. And then you go to the 50% column. So I'm in the third row here, and I go to the 50% column. It's all the way to the right, and you just pick the answer off of this. So it's 14 people. So notice this is split into two chunks. Think of it like this. There's two tables here. The top one is for 95%. The bottom one's for 99%. We're in the bottom table. The first row tells us how close we want to be to sigma, and then the last row tells us how many people we'd have to talk to. So we'd have to talk to 14 people, or survey 14 people, to be 99% confident and to be within 50% of the true standard deviation. Notice how much these numbers grow. So if I wanted to be 1% within sigma, I'd have to talk to 33,000 people, which is a huge number. But in this case, is 14 practical? Yeah, that's one of the easier numbers on here to talk to. So is the size practical? Yes. Because the sample size is small enough to be practical for most applications. B. Okay, next one. Similar to this. Assume that the sample is simple random, obtained from a normally distributed population of flight delays at an airport. Use the table below to find the minimum sample size needed to be 95% confident. So we're in the top part of the table. We're up here. That the sample standard deviation is within 10%. So top table, 10%. We're here. And the answer would be 192. So we'd have to talk to 192 people, or I would say talk to. We'd have to sample 192 flights to be 95% confident in our answer and have it be within 10% of the population standard deviation. A histogram of a sample of those arrival delays suggests that the distribution is skewed, not normal. How does the distribution affect the sample size? So we had said to do this math, we had to have a strict requirement on it being normal. So this math relies strictly on a population that is normal. If they're telling us it's skewed, not normal, this whole math breaks down. So we're going to say D, the computed minimum sample size is not likely correct. So in that case, don't necessarily trust your answer because the whole shape broke down on us. Okay, for 28, fill in the blank. The blank distribution is used to develop confidence interval estimates of variances, which are sigma squareds, or standard deviation, which are sigmas. Well, what have we been talking about all day? It's the chi-square. 29. Fill in the blank. The best point estimate of the population variance is the blank. We always use samples to predict population. So the best estimate of a population variance is a sample variance. And the symbol for sample variance is S squared. So it would be this one here, sample variance S squared. Okay, last one. Which of the following is not a requirement of constructing a confidence interval estimate for a population variance? The sample is a simple random sample. If you go back to all those problems we read today, they all said simple random sample. True. A histogram of the data must be bell-shaped. So we said you have to have a normal curve to do this data. That's true. The population must have normally distributed values. B and C are saying the same thing. True. The population must be skewed to the right. The distribution we use to solve this is skewed to the right, but we don't want the population to be skewed to the right. So this one's the one that doesn't belong. And now we'll complete section 7.3 and chapter 7.